Hello everyone. Can you hear me? Okay. I'm going to be reading about operating systems again. And last stream, I read about segmentation and this free space management. This stream, I'll be learning about introduction to paging and maybe this chapter as well, if I'm in the mood. Okay. Paging introduction. It is sometimes said that the operator system takes one of the two approaches when solving most any space management problem. The first approach is to chop things up into variable sized pieces, as we saw with segmentation in virtual memory. Unfortunately, the solution has inherent difficulties, in particular, when dividing a space into different sized chunks. The space itself can become fragmented, and thus allocation becomes more challenging. It is worth considering the second approach to chop up the space into fixed size pieces. In virtual memory, we call this idea paging, and it goes back to an early and important system, the Atlas. Instead of splitting up a process's address space into a number of variable sized logical segments, we divide it into fixed sized units, of which we call a page. Correspondingly, we view physical memory as an area of fixed size slot called page frames. Each of these frames can contain a virtual memory page. Our challenge: how can we virtualize the memory with pages so as to avoid the problems of segmentation? What are the basic techniques? A simple example. To help make this approach more clear, let's illustrate it with a simple example. Figure 18.1 presents an example of a tiny address space, only 64 bytes total in size with 416-byte page. Okay, this is the physical address. These are all the page frames for each of the virtual memory. Real address spaces are much bigger, of course, commonly 32 bits and thus 4 GB of address space, or even 64 bits. In the book, we will often use tiny examples to make them easier to digest. Physical memory, as shown in 18.2, is 0, 16, 32, 48. This is also all the way till 128. A 64-byte address space in a 128-byte physical memory. Physical memory, as shown in figure 18.2, also consists of a number of fixed sized slots. In this case, 8 page frames. And, okay, and frame 0 is for the OS. As you can see in the diagram, the pages of the virtual address space have been placed at different locations throughout physical memory. The diagram also shows the OS using some of the physical memory for itself. Paging, as we will see, has a number of advantages over our previous approaches. Probably the most important improvement will be flexibility. With a full developed paging approach, the system will be able to support the abstraction of an address space effectively. Regardless of how a process uses the address space, we won't, for example, make assumptions about the direction the heap and stack grow and how they're used. So, is it like one page frame for the code, one page frame for the heap, one page frame for the stack? Is it like that? Another advantage is the simplicity of free space management that paging affords. For example, when the OS wishes to place our tiny 64-byte address space into our 8-page physical memory, it simply finds 4 free pages. 64-byte address space into 8-page physical memory simply finds 4 free pages. Perhaps the OS keeps a free list of all the pages for this and just grabs the first 4 free pages of the list. In the example, the OS has placed virtual memory 0 of the address space in physical frame 3. Okay, 3 over here. So at the end of the page, do they have like a pointer going to the next page? To record where each virtual page of the address space is placed in physical memory, the operating system usually keeps a per process data structure known as a page table. The major role of the page table is to store address translations for each of the virtual pages of the address space, thus letting us know where in physical memory each page resides. For our simple example, the page table uh, thus have the following 4 entries. So virtual page 0, physical frame 3. Oh, so virtual frame page, physical frame. But what if there's a system, like there's a piece of code that takes the frame as input and wants to see which page of virtual memory there is? Would it have to like loop through all of these to find which frame is associated with which virtual page? It is important to remember that this page table is a per process data structure. Most page table structures we discuss are per process structures. An exception we will touch on is the inverted page table. If another process were to run in our example above, the OS would have to manage a different page table for it, as its virtual pages obviously map to different physical pages. Now we know enough to perform an address translation example. Let's imagine the process with that tiny address space is performing a memory access. Uh, okay, so virtual address goes into register EAX. Specifically, let's pay attention to the explicit load of the data from virtual address into register EAX. To translate this virtual address that the process generated, we have to first split it into two components, the virtual page number, VPN, and the offset within the page. For this example, because the virtual address space of the process is 64 bytes, we need 6 bits total for our virtual address. Thus, our virtual address can be conceptualized as follows. So, virtual address 5 for in this diagram, VA5 is the highest order bit of virtual address and VA0 is the lowest order bit. Because we know the page size, we can further divide the virtual address as follows. VPN and offset. So what is this exactly? This is the virtual address, right? This is 6 bits. So offset over here, VPN over here. We need 6 bits total for our virtual address. Because the virtual address of the process is 64 bytes, Okay, they need 6 bits. And so why is this VPN and this 16? Page size is 16 bits, 16 bytes. Okay, so one page. And okay, I think so. This VPN is like either it's page 0, page 1, page 2, page 3, like that. And the offset is within the page. Because there's 16 bytes on the page, we can use the offset to go within these 16 bytes. The page size is 16 bytes and a 64 byte address space, and thus we need to be able to select 4 pages and the top 2 bits of the address space just do just that. Thus, we have a 2-bit virtual page number, and the remaining bit tells us which byte of the page we are interested in. 4 bits in this case. When a process generates a virtual address, the OS and the hardware must combine to translate it into meaningful physical address. For example, let us assume the load above was to virtualize address 21. Okay, 0, 16. So address 21. It's a virtual address 21. So 0. So in the virtual address, the 48 byte is the 0 byte, right? And 48 plus 21, that gives 69. So that will go to, no wait. Yeah, that should go to page 1. Because this would be byte 6, byte, what would this be? This would be byte 16, right, in the virtual address. Turning 21 into binary form, we get 010101. Thus, we can examine this virtual address and see how it breaks down into virtual page number and offset. Uh, the virtual address 21 is on the 5th byte of the virtual page. With our virtual page number, we can now index our page table and find which physical frame virtual page 1 resides within it. So this is 1, so it's in page 1. Earlier I said 69. What's 69 minus 64? It's 5, right? So 16 from here. So what we are starting from here, the offset would be 16 from here and then 5 from here. And then we get our virtual address. In the page table above, the physical frame number, also sometimes called the physical page memory, is 7. A physical page number is 7. Thus, we can translate this virtual address by replacing VPN with the PFN and then issue the load to physical memory. Now the offset stays the same because the offset just tells us which byte within the page we want. Our physical memory address is now 110101. This is exactly where we want our load to fetch data from. Okay, so the offset within page 1 is 5. So 112 plus 5 would be 117, and that's where the physical address is. And in the virtual address, that would be 21. So, where are page tables stored? Page tables can get terribly large, much bigger than the small segment table or basebound pair we have discussed previously. For example, imagine a typical 32-bit address space with 4 KB pages. This virtual address splits into a 20-bit VPN and 12-bit offset. Recall that 10-bit would be needed for a 1 KB page size and just 2 more to get 4 KB. A 20-bit VPN implies that there are 2 to the power of 20 translations that the OS would have to manage for each process. Assuming we need 4 bytes per page table entry to hold the physical translation plus any other useful stuff, we will get an immense 4 megabyte of memory needed for each page table. That is pretty large. Now imagine there are 100 processes running. This means the OS would need 400 megabyte of memory just for all those address translations. In a modern era where machines have gigabytes of memory, it seems a little crazy to have large chunk of it just for translations, no? And when we think about how big such a page table would be for a 64-bit address space, that would be too gruesome. One of the most important data structures and memory management subsystem of the modern OS is the page table. In general, a page table stores virtual to physical address translations, thus letting the system know where each page of an address space actually resides in physical memory. Because each address space requires such translations, in general, there is one page table per process in the system. The exact structure of the page table is either determined by the hardware or can be more flexibly managed by the OS. Wait, where is figure 18.4 used? Did I miss it? Oh, it's here. Because page tables are so big, we don't keep any special on-chip hardware in the MMU to store page table of the currently running process. Instead, we store page table for each process in memory somewhere. Let's assume for now that the page tables live in physical memory that the OS manages. Later, we will see that much of the OS memory itself can be virtualized, and thus page tables can be stored in OS virtual memory. But that is too confusing right now, so we'll ignore it. In figure 18.4 is a picture of a page table in OS memory. So page table 3752. What is 3752? Oh, no, wait. Yeah, 3752. What's actually in the page table? Let's talk a little more about page table organization. The page table is just a data structure that is used to map virtual addresses to physical addresses. Thus, any data structure could work. Our simplest form is called a linear page table, which is just an array. The OS indexes the array by the virtual page number and looks up the page table entry at that index in order to find the desired physical frame number. For now, we will assume this simple linear structure. In later chapters, we will make use of more advanced data structures to help solve some problems with paging. As for the contents of each page table entry, we have a number of different bits in there worth understanding at some level. A valid bit is common to indicate whether the particular translation is valid. For example, when program starts running, it will have code and heap at one end of its address space and the stack at the other. Okay, wait, hold on. So address space of a process. The code is stored here. Heap is stored here. And the stack is on the other end. All of the unused space in between will be marked invalid, and if the process tries to access such memory, it will generate a trap to the OS, which will likely terminate the process. Thus, the valid bit is crucial for supporting a sparse address space. By simply marking all the unused pages in the address space invalid, we remove the need to allocate physical frame for those pages and thus save a great deal of memory. Now, what is all this? PFN is page physical frame number, right? So for a particular address, so page 0, the frame number is 3. Page 1, the frame number is 7. That's what I'm imagining. What is all this though? We might also have protection bits indicating whether the page could be read from, written to, or executed from. Again, accessing a page in a way not allowed by these bits will generate a trap to the OS. There are a couple of other bits that are important, but we won't talk about much for now. A present bit indicates whether this page is in physical memory or on disk. We will understand this machinery further when we study how to swap parts of the address space to disk to support address spaces that are larger than physical memory. Swapping allows the OS to free up physical memory by moving rarely used pages to disk. A dirty bit is also common, indicating whether the page has been modified since it was brought into memory. A reference bit is sometimes used to track whether a page has been accessed, and is useful in determining which pages are popular and thus should be kept in memory. Such knowledge is critical during page replacement, a topic we'll study in great detail. Figure 18.5 shows an example of a page table entry from an x86 architecture. It contains a present bit P, a read-write bit, which determines if writes are allowed to this page, a user supervisor bit, which determines if the user mod processes can access the page, a few bits that determine how hardware caching works for these pages. Okay. You may notice that in the Intel example, there are no separate valid and present bit, but rather just a present bit. If that bit is set, it means that the page is both present and valid. If not, it means that the page may not be present in memory but is valid, or may not be valid. And access to the page with p is equal to 0 will trigger a trap to the OS. The OS must then use additional structures it keeps to determine whether the page is valid or not. This sort of judiciousness is common in hardware, which often just provides a minimal set of features upon which the OS can build a full service. With page tables in memory, we already know that they might be too big. As it turns out, they can slow things down. For example, take our simple instruction. Again, let's just examine the explicit reference to address 21 and not worry about the instruction fetch. In this example, we'll assume hardware performs the translation for us to fetch the desired data, the system must first translate the virtual address 21 into the correct physical address 117. Thus, before fetching the data from address 117, the system must fetch the proper page table entry from the processor's page table, perform the translation, and then load the data from physical memory. To do so, the hardware must know where the page table is for the currently running process. Let's assume for now that the single page table base register contains the physical address of the starting location of the page table. To find the location of the desired PTE, the hardware will thus perform the following functions. So VPN, virtual address, VPN mask, shift, and then PT address, page table base register plus VPN, and size of PTE. Page table entry. So it not only needs to look for the address within the page table, but it also needs to find the page table itself. An example, VPN mask would be set to hex 30, which picks up the VPN bits from the full virtual address. Shift is set to 4, the number of bits in the offset, such that we want to move the VPN bits down to form the correct integer of virtual page memory. If they did not do VPN mask, if they just do shift, wouldn't all of these ones and zeros over here just go away? Or would they like wrap around? For example, with the virtual address 21 and a masking turns it into a value of 010000, the shift turns it into 01. But why even do the masking? Can't we just do the shift and it will become 01? Or a virtual page 1 as desired. We then use this value as an index into the array of PTEs, pointed to by the page table base register. A page table is stored at the top right. Yeah, it's stored over here. Um, I'm scrolling with the touchpad, that's why it suddenly goes up. Anyways, fetch the PTE, extract the PFN, and concatenate it with the offset from the virtual address to form the desired physical address. Specifically, you can think of PFN being left shifted by shift, and then otherwise ORed with the offset to form the final address as follows. Virtual address, offset mask. Is the offset mask to make sure that it's the correct size? Because this here is 2 bits. Physical address, PFN, shift. PFN is physical frame number. They're shifting it to put it over here, right? To put it as the 2 most significant bit in 6 bits. Then we are ORing it with offset. Okay. Oh, so then we are left with the physical address. So offset PFN. Hold on. Virtual address offset mask. Finally, the hardware can fetch the desired data from memory and put it into register EX. The program has now succeeded at loading a value from memory. To summarize, we now describe the initial protocol for what happens on each memory reference. Figure 18.6 shows the approach for every memory reference. Uh, Paging requires us to perform one extra memory reference in order to first fetch the translation from the page table. That is a lot of work. Okay, there is a lot. Extra memory references are costly and in this case will likely slow down the process. And now you can hopefully see that there are two real problems that we must solve. Without careful design of both hardware and software, page tables can cause the system to run slowly, as well as take up too much memory. Before closing, we now trace through a simple memory access example to demonstrate all of the resulting memory accesses that occur when using paging. The code snippet in C call in a file called array.c that we are interested in is as follows. So we compile array.c and run it with the following command. Of course, to truly understand what memory accesses this code snippet will make, we will have to know a few more things. First we have to disassemble the resulting binary to see what assembly instructions are used to initialize the array in a loop. Here is the resulting assembly code. So mobile. The code, if you know a little x86, is actually quite easy to understand. The first instruction moves the value 0 into the virtual memory address of the location of the array. This address is computed by taking the contents of EDI and adding EAX multiplied by 4 to it. Thus, EDI holds the base address of the array, whereas EAX holds the address index, array index. So, okay, so each value is 4 bytes, right? We're assuming that it's 4 bytes. Offset, starting, and then offset is multiplied by 4. We multiply by 4 because the array in the array of integers, each of size 4 bytes. The second instruction increments the array held in AAX, and the third instruction compares the contents of that register to the hex value 03E8 or decimal 1000. Okay, sorry. I get confused between control and shift. Uh, if the comparison shows that two values are not equal yet, which is what the jump not equal instruction test, the fourth instruction jumps back to the top of the loop. Okay, so it compares this. If they're not equal, then it jumps back to 1024. So it's the for loop, right? this for loop. Yeah, it just assigns 0 to all of them. To understand which memory accesses this instruction sequence makes we'll have to assume something about where in a virtual memory the code snippet and array are found, as well as the contents and location of the page table. For this example, we assume a virtual address space of size 64 KB. We will also assume a page size of 1 KB. All we need to know now are the contents of the page table and its location in physical memory. Let's assume we have a linear array based page table and that it is located at a physical address 1 KB. As for its contents, there are just a few virtual pages we need to worry about having mapped for this example. First, there's a virtual page the code lives on because the page size is 1 KB. The virtual address 1024 resides on the second page. So the virtual address space is 64 KB and page size is 1 KB. Located at a physical uh, assume we have a linear array based page table at 1 KB. Okay, wait, hold on. A virtual address space of 64 KB. '64. We will also assume a page size is 1 KB. I'll just draw some lines. So 0, 1, 2, 3, 4. So each page page size is 1 KB. Page table and that it is located at physical address 1 KB. Okay, so um all of this is for reserved for the OS. Page table is over here. Page table. Over. I just want to draw an arrow. Yeah. Page at byte 1 starts. As for its contents, there are a few virtual pages we need to worry about having mapped for this example. Once there's a virtual page that the code lives on, because the page size is 1 KB, the virtual address 1024 resides on the second page of the virtual address space. VPN 1, as VPN 0 is the first page. The first page, wait, hold on. In the physical address 1 KB is where the page table starts. Uh, Virtual address. In the virtual address 1024 resides on the second page of the virtual address space. Let's assume this virtual page maps to physical frame 4. Okay, so we have this. This maps to this. Okay. Next, there is the array itself. Its size is 4000 bytes, and we will assume that it is resides at virtual address 4000 through 44 no 40,000 through 440 44,000, not including the last byte. The virtual pages for this decimal range are VPN 39 to VPN 42. Wait, let me think. 39, 39, all the way till 39, 42. Thus, we need mappings for these pages. Let's assume these virtual to physical mappings for the example. So 39 goes to 7, 40 goes to 8, 9, and 10. Hold on. 4, 5, 6, 7, 8, 9, 10, 11. Why is this doing this? This goes here. This goes here. And 39 goes to 7. 42 goes to 10. Now what? We are now ready to trace memory references of the program. When it runs, each instruction fetch will generate two memory references, one to the page table to find the physical frame that the instruction resides within, one to the instruction itself to fetch it to the CPU for processing. In addition, there is one explicit memory reference in the form of the move instruction. This adds another page table access to translate the array of virtual addresses to the correct physical one. Then the array access itself. The entire process for the first five loop iterates. It is depicted in figure 18.7. So page table 139. The bottommost graph shows the instruction memory references on the y-axis in black. With virtual addresses on the left and actual physical addresses on the right. The middle graph shows array accesses in gray again in a dark gray, again with the virtual on left and physical on right. The x-axis for the entire trace shows memory accesses across the first five iterations of the loop. Finally, the topmost graph shows the page table memory accesses in the light gray. The x-axis for the entire trace shows memory accesses across the first five iterations of the loop. There are 10 memory accesses per loop, which includes 4 instruction fetches, 1 explicit update of memory, and 5 page table accesses to translate those 4 fetches and 1 explicit update. See if you can make sense of the patterns that show up in this visualization. In particular, that will change as the loop continues to run beyond the first 5 iterations. This has been the simplest of examples, yet you might already be able to sense the complexity of understanding the actual memory behavior of real applications. Don't worry, it definitely gets worse because the mechanism we are about to introduce only complicated this already complex machine. Yeah, I did not understand this bit. Okay, I will just read this chapter and I will end the stream. Faster translations. Using paging as a core mechanism to support virtual memory can lead to high performance overhead. By chopping the address space into small fixed size units, paging requires a large amount of mapping information. Because that mapping information is generally stored in physical memory, paging locally requires an extra memory lookup for each virtual address generated by the program. Going to memory for translation information before every instruction fetch or explicit load is in or store is prohibitively slow, and that's our problem. How can we speed up address translation and generally avoid the extra memory reference that paging seems to require? What hardware support is required? What OS involvement is needed? When we want to make things fast, the OS usually needs some help. And help often comes from the OS's old friend, the hardware. To speed address translation, we are going to add what is called a translation loci buffer or TLB. A TLB is part of the chip's memory management unit and is simply a hardware cache of popular virtual to physical address translations. And thus, a better name would be an address translation cache. Upon each virtual memory reference, the hardware first checks the TLB to see if the desired translation is held therein. If so, the translation is performed quickly without having to consult the page table. Because the tremendous performance impact, TLBs in a real sense make virtual memory possible. TLB control flow algorithm. So the basic algorithm, figure 19.1, shows a rough sketch of how hardware might handle virtual address translation, assuming a simple linear page table and a hardware managed TLB. The algorithm and the hardware follows works like this. First, extract the virtual page number from the virtual address. Okay. Uh, and check if the TLB holds the translation for this VPN. Yeah. If it does, we have a TLB hit, which means TLB holds the translation success. We can now extract the page frame number and from the relevant TLB entry, concatenate that onto the offset from the original virtual address and form the desired physical address. And access memory, assuming protection checks do not fail. If the CPU does not find translation in the TLB, we have some more work to do. In this example, the hardware accesses the page table to find the translations, and assuming that the virtual memory reference generated by the process is valid and accessible, updates the TLB with the translation. These set of actions are costly primarily because of the extra memory references needed to access the page table. Finally, once the TLB is updated, the hardware retires the instruction. This time, the translation is found in the TLB and the memory reference is processed quickly. Okay, so VPN, virtual address, VPN mask, and shift. TLB lookup. Is it a success? If it is, get the physical address. If not, PDE address, page table entry address. Okay, this is quite confusing. The TLB, like all caches, is built upon the premise that in the common case, translations are found in the cache. If so, a little overhead is added as the TLB is found near the processing core and is designed to be quite fast. When a miss occurs, the high cost of paging is incurred and the page table must be accessed to find the translation. An extra memory reference results. This happens often. The program will likely run noticeably more slow. Memory accesses relative to most CPU instructions are quite costly. TLB misses lead to more memory accesses. Thus, it is our hope to avoid TLB misses as much as we can. To make clear the operation of TLB, let's example a simple virtual address trace and see how a TLB can improve its performance. In this example, let's assume we have an array of 10 4-byte integers in memory, starting at virtual address 100. Okay. In the address space, virtual address 100. Starting here, we have from here to 101. We have one number. And from 101 to 102, we have another number. 102 to 103, we have another. So 1, 2, 3, 4. We have an array of 10 4-byte integers in memory. Oh, so it's not 100, it's like 104, 108, and so on. All the way till there are 10 integers, right? So there are 10 storage. Assume further that we have a small 8-bit virtual address space with 16-byte pages. Thus, virtual address breaks down into a 4-bit VPN. There are 16 virtual pages and a 4-bit offset. There are 16 bits on each of those pages. Okay, wait. So this time it's stored like 1, 2, 3, 4. One, two, three, four, 1, 2, 3, 4. Okay, so the address space is 8-bit. You're using 8-bit for the entire address space, and it's divided into 16 pages. 16 virtual pages. 8-bit virtual address space. Four-bit VPN, 4-bit offset. So this is the VPN. This is the offset. Figure 19.2 shows the array laid out on the 16-byte pages of the system. I think they meant 16 by 16. So virtual page number 16 bytes. You have an array of 10 4-byte integers. Okay, so one integer here, one here, one here, one here. So this is one page, this is another page, this is another page. They go on different part of the physical address. I mean in different pages. As you can see, the array's first entry begins on VPN 6 and offset 4. Only 3 4-byte integers fit onto that page. Shouldn't all of it start at 0? Why would it start with an offset? The array continues onto the next page. There are 4 where the next 4 entries are found. Finally, the last three entries of the 10 entry array are located on the next page of the address space. Let's consider a simple loop that accesses each array element, something that would look like this in C. Let me see. For the sake of simplicity, we will pretend that the only memory accesses the loop generates R to the array, ignoring the variables I and the sum as well as the instructions themselves. When the first array element A0 is accessed, the CPU will see a load of virtual address will see a load to virtual address 0. Wait, hold on. So this over here is 0, right? This is 16. 1, 2, 3, 4, 5, 6. So at the end, we reach 96. And then plus 4 will be 100. Oh, so that's why the offset is 3. The address, yeah, the address is 0. I forgot about that. Virtual address 100. The hardware extracts the VPN from this, which is 6, and uses that to check the TLB for a valid translation. Assuming this is the first time the program accesses the array, the result will be a TLB miss. What's the full form of TLB again? Translation loci buffer. So it's like a cache for virtual to page entry. It's like a cache for translation. The next access is A1, and there is good news here. A TLB hit because the second element of the array is packed next to the first. It lives on the same page because we have already accessed this page. When accessing the first element of the array, the translation is already loaded into the TLB, and hence the reason for our success. Access to A2 encounters a similar success because it too lives on the same page as A0 and A1. To watch an when the page accesses A3, we encounter another TLB miss. However, once again, the next entries A4 to A6 will hit in the TLB as they all reside on the same page in memory. A7 causes one last TLB miss. The hardware once again consults the page table to figure out the location of this virtual page in physical memory and updates the TLB accordingly. The final two accesses uh, receive the benefits of this TLB update. The hardware looks on the TLB for their translations. Two more hits result. Let's summarize the TLB activity during our 10 accesses of the array. Miss hit hit, miss hit hit hit, miss hit hit. Thus, our TLB hit rate, which is the number of hits divided by the total number of accesses, is 70%. Although this is not too high, it is non-zero, which may be a surprise. Even though this is the first time the program accesses the array, the TLB improves performance due to spatial locality. The elements of the array are packed tightly into pages. They are close to one another in space, and thus only the first access to an element on a page yields a TLB miss. Also note that the page size plays in this example. If the page size had simply been Had simply been twice as big, the array access would suffer even fewer misses, as typical page sizes are more like 4 kilobyte. These types of dense array-based accesses achieve excellent TLB performance, encountering only a single miss per page of accesses. One last point about TLB performance. If the program soon after this loop completes, accesses the array again, we will likely see an even better result, assuming that we have a big enough TLB to cache the needed hit translations. In this case, the TLB hit rate would be high because of the temporal locality, the quick re-referencing of memory items and time. Like any cache, TLBs rely upon both spatial and temporal locality for success, which are the program properties. If the program of interest exhibits such locality, the TBL hit rate will likely be high. Caching is one of the most fundamental performance techniques in computer systems, one that is used again and again to make the co- uh, common case fast. The idea behind hardware caches is to take advantage of locality in instruction and data references. There are usually two types of locality: temporal locality and spatial locality. With temporal locality, the idea is that an instruction or data item that has been recently accessed will likely be reaccessed soon in the future. Think of loop variables or instructions in a loop. They are accessed repeatedly over time. With spatial locality, the idea is that if a program accesses memory address X, it will likely soon access a memory near X. Imagine here streaming through an array of some kind, accessing one element and the next. Of course, these properties depend on the exact nature of the program and thus are not hard and fast laws, but more like rules of thumb. Hardware caches, whether for instruction data and or address translations, take advantage of locality by keeping copies of memory in small, fast on-chip memory instead of having to go to a slow memory to satisfy a request. The process can first check if a nearby copy exists in a cache. If it does, the processor can access it quickly and avoid spending the costly time it takes to access memory. You might be wondering, if caches are so great, why don't we just make bigger caches and keep all of our data in them? Unfortunately, this is where we run into more fundamental flaws like those of physics. If you want fast cache, it has to be small, as issues like the speed of light and other physical constraints become relevant. Any large cache, by definition, is slow and thus defeats the purpose. Who handles the TLB mess? One question that we must answer: who handles a TLB mess? Two answers are possible: the hardware or the software. In the olden days, the hardware had complex instruction sets, sometimes called CISC for complex instruction set computers, and the people who built the hardware didn't much trust those sneaky OS people. Thus, the hardware would handle the TLB mess entirely. To do this, the hardware has to know exactly where the page tables are located in memory via a page table based register used in line 11 and figure 9.1, as well as their exact format. On a miss, the hardware would work the page table, find the correct page table entry, and extract the desired translation. Update the TLB with the translation and retry the instruction. Example of an older architecture that has hardware managed TLBs is the Intel x86 architecture, which uses a fixed multi-level page table. The current page table is pointed to by the CR3 register. More modern architectures, both RISC or reduced instruction set computers, have what is known as software managed TLBs. On a TLB miss, the hardware simply raises an exception which pauses the current instruction stream, raises the privilege level to kernel mode, and jumps to a trap handler. As you might guess, this trap handler is code within the OS that is written with the express purpose of handling TLB misses. When run, the code will look up the translation in the page table, use special privilege instructions to update the TLB, and return from the trap. At this point, the hardware retries the instruction. Let's discuss a couple of important details. First, the return from trap instruction needs to be a little different than the return from trap we saw before when servicing a system call. In the latter case, the return from trap should resume execution at the instruction after the trap into the OS, just as a return from a procedure call returns to the instruction immediately following the call into the procedure. In the former case, when returning from a TLB mishandling trap, the hardware must resume execution at the instruction that caused the trap. This retry thus lets the instruction run again, this time resulting in a TLB hit. Thus, depending on how a trap or exception was caused, the hardware must save a different PC when trapping into the OS in order to resume properly when the time to do so arrives. Second, when running the TLB mishandling code, the OS needs to be extra careful not to cause an infinite chain of TLB messes to occur. Many solutions exist. For example, you keep TLB mishandlers in physical memory or reserve some entries in TLB for permanently valid translations and use some of those permanent translation slots for the handler code itself. These wide translations always hit the TLB. The primary advantage of the software managed approach is flexibility. The OS can use any data structure it wants to implement the page table without necessitating hardware change. Another advantage is simplicity. As seen in the TLB control flow, the hardware doesn't do much on the EMS, just raise an exception and let the OS TLB miss handler do the rest. Uh, A common mistake is to confuse the valid bits found in TLB with those found in page table. In a page table, when a page table entry is marked invalid, it means that the page has not been allocated by a process and thus should not be accessed by a correctly working program. The user response when an invalid page is accessed is to trap to the OS, which will respond by killing the process. A TLB valid bit, in contrast, simply refers to whether a TLB entry has a valid translation within it. When a system boots, for example, a common initial state for each TLB entry is to be set to invalid because no address translation are yet cached there. Once virtual memory is enabled and once programs start running, accessing their virtual address spaces, the TLB is slowly populated and thus valid entries soon fill the TLB. The TLB valid bit is quite useful when performing a context switch tool. As we discussed further below, by setting all TLB entries to invalid, the system can ensure that the about to be run process does not accidentally use a virtual to physical translation from a previous process. Let's look at the contents of the hardware TLB in more detail. A typical TLB might have 32, 64, and 128 or 128 entries and be what is called fully associative. Basically, this just means that any given translation can be anywhere in the TLB and that the hardware will search the entire TLB in parallel to find the desired translation. A TLB entry might look like this. So VPN, PFN, other bits. Note that both the VPN and PFN are present in each entry as the translation could end up in any of these locations. In hardware terms, the TLB is known as fully associative cache. The hardware searches the entries in parallel to see if there is a match. More interesting are the other bits. For example, the TLB commonly has a valid bit which says whether the entry has a valid translation or not. Also common in our protection bit, which determines how a page can be accessed. For example, code pages might be marked real and execute, whereas heap pages might be marked as read and write. There may be a few other fields, including an address space identifier, or a dirty bit, and so forth. TLB issue context switches. With TLBs, new issues arise when switching between processes. Specifically, the TLB contains virtual to physical translations that are only valid for the currently running process. These translations are not meaningful for other purposes. As a result, when switching from one process to another, the hardware or OS must be careful to ensure that the about to be run process does not accidentally use translation for some previously run process. To understand the situation better, let's look at an example. When one process is running, it assumes TLB might be caching translations that are valid for it. When one process is running, it assumes the TLB might be caching translations that are valid for it that come from P1's page table. Assume for this example that the 10th virtual page of P1 is mapped to physical frame 011. So this maps to this virtual page number, physical frame number. In this example, assume other process P2 exists and the OS soon might decide to perform a context switch and run it. Assume here that the 10th virtual page of P2 is mapped to physical frame 170. If entries for both processes were in TLB, the contents of TLB will look like this. In the TLB above, we clearly have a problem. VPN 10 translates to either 100 or physical frame number 100 or 170, but the hardware can't distinguish which entry is meant for which process. Thus, we need to do more work in order for the TLB to correctly and efficiently support virtualization across multiple processes. When you're context switching between processes, the translation in the TLB for the last process are not meaningful to be about to be run process. What should the hardware or OS do in order to solve this problem? There are a number of possible solutions to this problem. One approach is to simply flush the TLB on context switches, thus emptying it before running the next process. On a software-based system, this can be accomplished with an explicit hardware instruction. With the hardware managed TLB, the flush can be enacted when the page table-based register is changed. In either case, the flush operation simply sets all valid bits to 0, essentially clearing the contents of the TLB. By fetching the TLB on each context switch, we now have a working solution as a process will never accidentally encounter the wrong translations into TLB. However, there's a cost. Each time a process runs, it must incur TLB misses as it touches its data and code pages. If the OS switches between processes frequently, this cost may be high. To reduce this overhead, some systems add hardware support to enable sharing of TLB across context switches. In particular, some hardware systems provide an address space identifier field in the TLB. You can think of address space identifier as a process identifier, but usually it has fewer bits. If you take an example TLB from above and add address space identifier, it is clear processes can readily share the TLB. Only the address space identifier field is needed to differentiate otherwise identical translations. Here is a depiction of a TLB with the added address space identifier field. Thus, with the address space identifier, the TLB can hold translations from different processes at the same time without any confusion. Of course, the hardware also needs to know which process is currently running in order to perform translations, and thus the OS must, on the context switch, set some privilege register to the address space identifier of the current process. As an aside, you may also have thought of another case where two entries of the TLB are remarkably similar. In this example, there are two entries for two different processes with two different VPNs that point to the same physical page. This situation might arise, for example, when two processes share a page. In the example above, process 1 is sharing physical page 101 With process 2, P1 maps this page into the 10th page of its address space, whereas P2 maps it to the 50th page of its address space. Sharing of code pages is useful as it reduces the number of physical pages in use, thus reducing memory overheads. Okay, how much is left? I think this is the last, yeah. As with any cache, and thus also with the TLB, one more issue that we must consider is cache replacement. Specifically, when we are installing a new entry in the TLB, we have to replace an old one, and thus the question which one to replace. Which TLB entry should be replaced when we add a new TLB entry? The goal, of course, being to minimize the miss rate. We'll study such policies in some detail when we tackle the problem of swapping pages to disk. He will just highlight a few typical policies. One common approach is to evict the least recently used entry. Uh, it tries to take advantage of locality in the memory reference stream. Assuming it is likely an entry that has not recently been used is a good candidate for eviction. Another typical approach is to use a random policy which evicts TLB mapping at random. Such a policy is useful due to its simplicity and ability to avoid corner case behaviors. For example, a reasonable policy such as least recently used behaves quite unreasonably when a program loops over n plus 1 pages with a TLB of size n. In this case, least recently used misses upon every access, whereas random does much better. A real TLB entry. Finally, let's briefly look at real TLB. This example is from MIPS, a modern system that uses software managed TLBs. A slightly modified MIPS TLB entry can be seen in figure 19.4. The MIPS R4000 supports a 32-bit address space with a 4 kilobyte page. With 4 kilobyte pages. Thus, we would expect a 20-bit VPN, alright, 12-bit offset in a typical virtual address. However, as you can see in the TLB, there are only 19 bits for the VPN. As it turns out, user addresses will only come from half the address space. The rest is reserved for the kernel, and hence only 19 bits of VPN are needed. The VPN translates to up to 24 bits of physical frame number, and hence can support systems with up to 64 gigabytes of physical main memory. There are a few interesting bits in the MIPS TLB. We see a global bit, which is used for pages that are globally shared among processes. Thus, if a global bit is set, the ASID is ignored. We also see the 8-bit ASID, which the OS can use to distinguish between address spaces as described above. One question for you: what should the OS do if there are more than 256 processes running at a time? Finally, we see three coherence bits which determine how a page is cached by the hardware. A bit beyond the scope of these notes, a dirty bit which is marked when the page is written has been written. A violet bit which tells the hardware if there is a valid translation present in the entry. There is also a page mask field. It supports multiple page sizes. We will see later why having larger page sizes might be useful. Finally, some of the 64 bits are unused. MIPS TLBs usually have 32 or 64 of these entries, most of which are used by the user process as they run. However, a few are reserved for the OS. A wide register can be set by the OS to tell the hardware how many slots of TLB to reserve for the OS. The OS uses these reserve mappings for code and data that it wants to access during critical times, where a TLB miss would be problematic. Because the MIPS TLB is software managed, there needs to be instructions to update the TLB. The MIPS provides four such instructions. TLBP, which probes the TLB to see if a particular translation is in there. TLBR, which reads the contents of the TLB entry into registers. TLBWI, which replaces a specific TLB entry. And TLBWR, which replaces a random TLB entry. The OS uses these instructions to manage TLB's contents. It is, of course, critical that these instructions are privileged. Imagine, okay. The term random access memory or RAM implies that you can access any part of the RAM just as quickly as another. While it is generally good to think of RAM in this way because of hardware features such as TLB, accessing a particular page of memory may be costly, particularly if that page isn't currently mapped by your TLB. Thus, it is always good to remember that the implementation tip RAM isn't always RAM. Sometimes randomly accessing your address space, particularly with the number of page access exceeds the TLB coverage, this can lead to severe performance penalties because one of the advisors, David Curler, used to always point to TLB as a source of many performance problems. We named this law in his honor Curler's law. Okay. Summary. We have seen how hardware can help us make address translation faster by providing a small dedicated on-chip TLB as an address translation cache. Most memory references will hopefully be handled without having to access page table in main memory. Thus, in the common case, the performance of the program will be almost as if memory isn't being virtualized at all. An excellent achievement for an operating system and is certainly essential to use the paging in modern systems. TLBs do not make world rosy for every program that exists. In particular, if the number of pages a program accesses in a short period of time exceeds the number of pages that fit into the TLB, the program will generate a large number of TLB misses and thus run quite a bit more slowly. If we refer to this phenomenon as exceeding the TLB coverage, and it is quite a problem for certain programs. One solution, as we discuss in the next chapter, is to include support for larger page sizes. By supporting key data structures into regions of the program's address space that are marked by larger pages, the effective coverage of the TLB can be increased. Support for large pages is often exploited by programs such as database management system, which has certain data structures that are both large and randomly accessed. One other TLB issue worth mentioning, TLB access can easily become a bottleneck in the CPU pipeline, in particular with what is called a physically indexed cache. With such a cache, address translation has to take place before the cache is accessed, which can slow things down quite a bit. Because of this potential problem, people have looked into all sorts of clever ways to access cache with virtual addresses, thus avoiding the expensive step of translation in the case of cache hit. Such a virtually indexed cache solves some performance problems, but introduces new issues into hardware design as well. Okay, I'll end the stream here then. And yeah, next stream I will start studying advanced speech. I did not I'm still confused about some of the core concepts. And in the latest section of paging, I got a little confused there as well. Okay, I will read the next two chapters on the next stream, I guess. Anyways, I will see you guys next time then. Bye.